Hello everyone, I welcome you all to learn about the Ellingham diagram that is based on the thermodynamic properties of reduction of metal oxides. So let's begin. So first, let us revise some of the important thermodynamic parameters that will be used to understand the Ellingham diagram. So let's start with delta G. It is the change in the Gibbs free energy that takes place in a chemical reaction. Next, we have delta S, that is the change in the entropy that takes place during the conversion of reactants to product. S, that is the entropy, is the measure of randomness or disorder. Then we have delta H, that represents the change in the enthalpy of the system in the reaction. So the relation between these three thermodynamic parameters at a given temperature can be given by the equation delta G is equals to delta H minus T delta S. Over here, the T is given in Kelvin. And we know that if the delta G is negative, then the reaction is said to be spontaneous. Whereas if it's positive, then it's said to be non-spontaneous. So what exactly is Ellingham diagram? The graphical representation of Gibbs free energy versus temperature helps us to predict the feasibility of the thermal reduction of an ore, and that is known as the Ellingham diagram. It was first given by H.J.T. Ellingham. So why do we take Gibbs free energy into consideration? That is because the extraction of metals from the metal oxide by reduction process using suitable reducing agent or thermal decomposition is based on the Gibbs free energy. So this is how the Ellingham diagrams looks like. On x-axis, we have temperature that is given in Kelvin. On y-axis, we have delta G that is given in kilojoules per mole. Now let us discuss about some of the basic reactions that we'll need to understand Ellingham diagram and how the delta G varies with different types of reactions. So let us start with the reaction of the combustion of metal and the formation of metal oxides. So this is how we give the reaction of the combustion of metals. So the metal reacts with oxygen to give metal oxides. For combustion reactions are considered to be exothermic, and so delta H is always negative for these reactions. Over here, delta S is negative as the gas is converted into solid and the randomness decreases. So for the given equation, we can say that delta G increases with increase in temperature. Next, let us have a look to the formation of carbon monoxide. So this is the reaction of formation of carbon monoxides. Over here also delta H is negative, but here delta S is positive as the volume of the gaseous product is more than the volume of the gaseous reactant. So for the given equation, T delta S becomes negative, and so we can conclude that delta G decreases with the increase in temperature. Next, let us have a look to the formation of carbon dioxide. This is the reaction of the formation of carbon dioxide. Over here also delta H is negative, but over here delta S is almost zero, and that's because the gaseous component in the reactants and the products is almost the same. So in this case, T delta S becomes zero for the given reaction, and that's why we can conclude that delta G doesn't vary much with the change in temperature. So let us learn about the characteristics of reduction of metal oxides. So for a metal oxide to reduce to give the final metal using reducing agent, it is very necessary that the reactions should be spontaneous. That is, delta G should be negative. So let us now take an example of reduction of metal using carbon. So this is the reaction. That is when metal oxide reacts with carbon, it gives metal plus carbon monoxides. Over here, carbon monoxide is more stable than the metal oxides, and that's why carbon is able to reduce the metal oxides and the reaction is said to be spontaneous. So what we can conclude from the earlier reactions? We can say that if the metal oxide is more stable than the oxide of the reducing agent used, then the metal oxide doesn't get reduced to give free metal. The second thing that we can conclude is the value of delta G should be negative, and more negative the value of delta G, greater will be the tendency of the metal oxide to get reduced. So Ellingham diagram plays an important role in helping us find out the suitable reducing agent for particular metal oxides, as it plots the change in the free energy against temperature for the reaction of metals and other elements at 1 atmospheric pressure with 1 mole of gaseous oxygen. So now we'll start with the characteristics of Ellingham diagram. So the first point that we need to notice is that for most of the metal oxide formation, we see a straight line with upward slope, that is a positive slope. The positive slope indicates the decrease in stability of the metal oxide with increase in temperature. They are stable till the point where delta G is negative as indicated, above which the metal oxides are unstable and decomposes on their own. The second thing that we need to notice is that for some metal oxides, we can see a sudden change in the slope like silver oxide, cupric oxide, zinc oxide, magnesium oxide. This is because the sudden phase change that is seen from solid to liquid or to liquid to vapor. The third thing that we need to notice that some metal oxide formation here, silver oxide, reactions are closer to the top of the diagram, indicating noble metals. These metal oxides are highly unstable and therefore can be easily reduced. The fourth thing that we need to observe is that for formation of carbon dioxide, the straight line is parallel to the temperature axis. This tells us that delta G doesn't vary much with the change in the temperature, as we have seen earlier while discussing about the reactions. The fifth thing, which is very important, is that for formation of carbon monoxide, the straight line is with a negative slope. This indicates that CO2 becomes more stable with increase in temperature as the delta G decreases. This is exactly opposite to what is the case with the metal oxide. So now let us see what are the things that we need to remember truly from Ellingham diagram. So as we move towards the bottom of the diagram, the metals are more reactive and it becomes harder to reduce their metal oxides. Carbon acts as a good reducing agent, as in the diagram. We can see that it cuts the line of many metals and can reduce them at sufficiently high temperatures. As now we have discussed about the features and significance of Ellingham diagram, let us have a look to the limitations of Ellingham diagram. So the first limitation is, as it is based on the thermodynamic concepts, it tells us about if the reactions are feasible or not. It doesn't indicate the rate of the reaction and also doesn't tell about the possibility of the other reactions taking place. The second thing is, for interpreting delta G, it is presumed that the reactants and products are in equilibrium, which is not true for all the conditions. Thank you for watching, everyone.